Welcome back to Nick's Algebraics. Today I'm going to talk about the kinematic equations and how to apply them. And you can check out the description if you want to follow along with the guided notes. So with me today, we got Random Guy,
Hello, I'm the most random of all the guys.
and we also have Peanut Butter Brother.
Yo, Wagwan fam. Make sure to like and subscribe, fam, or you're gonna catch a death house to your blood clot face, fam. Okay.
Let me start by asking, how much physics do you know?
I would say I have quite a nice repertoire. I'd say I'm very experienced in the physics space. I've crafted a few theories myself. I actually helped Einstein with a lot of his very big theories and a lot of his work. I have two PhDs. One in astrophysics, one in just regular good old physics. Taking a lot of different classes, and I would say I'm pretty qualified. So if you guys ever need any help, feel free to reach out in the comments. I will respond to you with some answers. So, yep.
Wonderful. So let's start by asking ourselves, what are the kinematic equations? The kinematic equations are a set of formulas that describe the motion of an object under constant acceleration. So in my last video, I used x1 for initial position and v1 for initial velocity of an object. But now I'm going to use x naught, x0, and v0 for the position and velocity at t equals 0. And at some time t, the position and velocity are called x and v.
Yeah, some people like to write an F subscript for final, but if you don't write it, it's just assumed. That's just the lingo in the academic circles. That's what the cool kids call it.
That's right. And I also have subscript x and y. So everything in this column right here is, if the motion is all horizontal, then all the subscripts are x. Like this is velocity in the x direction. This is, for example, initial velocity in the x direction. This is acceleration in the x direction. And everything in this column is for vertical motion. So all the subscripts are y because everything's happening in the y direction. One important thing to remember is that these kinematic equations can only apply to motion with constant acceleration. Acceleration has to equal some number. If that's not the case, you can't use these. Let's do an example. For example 1, we have a person standing on the roof of a 30-meter high building, and this guy throws a ball straight upward with an initial speed of 6 meters per second. After the ball is thrown, it is in free fall, and we're ignoring air resistance. On its way back down, it just misses the building. Compute the velocity of the ball 1 second after it was thrown. First thing I like to do is just draw a picture of what's
I was
happening.
about to suggest that very same thing.
Wonderful. So I'm going to draw the building. We have the person on the roof of the building.
Did they say how tall the person was, or were we just assuming it's negligible height?
Yeah, we're ignoring that.
Interesting, but the height is actually, I think, an interesting component to this. I think it does kind of affect it. No,
Is the person a particle or a wave?
Oh my God. That's a great
is
question.
it person aura or sigma?
Let's say this is the ball right here, and, he throws the ball straight upward. Again, we're ignoring this height right here. We can just pretend that he threw it from like here. Like he just threw.
Physics classes be like,
Yeah.
ignore everything.
Ignore all those complications. So the ball goes straight up. So something like this. I'm going to draw its trajectory in the red dashed line. And like the problem says, after the ball is thrown, it is in free fall. So it's going to go straight down. So just for clarity, instead of drawing it going straight down like that on top of the line, I'm going to draw a little curve like this. And then it goes straight down. This ball is totally just going up and coming back down. So this curve, this U-shaped curve is just there for clarity. It's not.
Explain why it magically doesn't hit the side of the building but falls to the ground.
Yeah, that's another thing. On its way back down, it just misses the building.
Maybe it got blown by that wind that we're ignoring.
Yeah.
Mm,
That wind we're ignoring definitely did that.
true. We should also calculate the probability that a bird comes in and flies and smacks the ball straight back at the person, and then factor that into the equation as well. That's kind of an important part of this problem, in my opinion.
Of course,
So,
of course.
you gotta think about these things, Nick. Come on.
There's too much magic for this problem to be a real physics problem. But go ahead.
Exactly.
Yes. So I will make the floor, like the ground, y equals 0. So we can choose which direction we want to be positive. So I'm going to choose up to be positive. So I'm going to do this. Up is the positive y direction.
What's the x coordinate? Left or right?
X coordinate doesn't matter because everything's.
I think we should still draw it, even if it doesn't matter.
I agree.
Nah, it's okay.
He just denied you. That's crazy.
Okay, so let's write down all our knowns. By the way, everything's vertical, so I'm going to use these equations right here. These are the
It's
same.
literally the same equations with different subscripts. It's the same thing.
Exactly, yeah. So we have the initial position, why not, is, it sounds like I'm saying why not, but it's like y0.
Do people even know that you don't spell it N-O-T?
A lot of people don't know that. It's not. It's not like that. It's like this, not.
Because physics teachers just start saying
Mm.
that, and then like they don't explain it at all.
Yeah,
But we're better on this channel. We explain things.
yes, yes. Every step is shown. So anyway, the initial position is 30 meters. We have the initial velocity in the y direction. I guess the initial speed is 6 meters per second.
I think we can say velocity in the positive y direction.
In this case, it's pretty much the same thing because it's going up. They're going to have the same magnitude, the speed and the velocity. We have also the time because we're trying to figure out what's the velocity 1 second after it's thrown. So we have t equals 1 second. And we have one more piece of information that's not exactly given.
Could I say it, or does Peanut Butter Brother want to say it since he has a PhD from Harvard?
If I told you the answer, how would that make you any better? You know, right?
That's
if I
true.
just give you all the answers to life, you're not going to improve. You're not going to evolve as a human being. So I want to give you the opportunity to improve yourself and answer this question here. So go ahead.
Look, so there's a gravitational field from the Earth that creates gravitational acceleration, in this case in the negative y direction, because gravity points downwards. We defined that variable to be g, which is, we treat approximately as constants 9.81 meters per second squared near the surface of the Earth. So we could say that acceleration in the y direction is equal to negative g.
Correct.
Well done.
So the problem says free fall. After the ball is thrown, it is in free fall. So that means that the acceleration is due to gravity, which is a constant. And near Earth's surface, the acceleration due to gravity is 9.81 meters per second squared. And since the acceleration is downward, that means we're going to say acceleration is negative g, so negative 9.81 meters per second squared.
I always leave it as g. Also, everybody, g is always positive.
Yes, g is 9.81, so we can say the acceleration is negative g, but I'm putting in the 9.81.
That's why it's important to draw that picture and draw those coordinate axes.
Here, I'll actually include acceleration here. This is the acceleration. I wrote down all the knowns, so now we have to figure out which equation we're going to use. So we're trying to find the velocity, specifically the final velocity right here. We want Vy.
I do want that. That is what I want.
Let's hope it wants you back. So
all physics is attracted to me because of the Higgs boson.
yes.
Good one.
Yes, yes. So this equation doesn't have final velocity in it, so we're not going to use that. We don't know the final position of the ball. So this equation has two unknowns. We don't know this. We don't know the final velocity. We don't know the final position. So I don't want to use this. Again, over here, we don't know the final position. We don't know the final velocity. So I'm not going to use this. But over here, we have initial velocity, we have acceleration, and we have time. So we can easily find final velocity using this first equation.
It doesn't have initial position in it, though, which we do know, but maybe we won't need that until a later part of the question.
Yeah, we'll use that eventually. So Vy equals V naught y plus AYT. The initial velocity, 6 meters per second. Acceleration in the y direction is negative 9.81 meters per second squared, and then times the time, which is 1 second. So notice how we have meters per second squared times second. That means it's going to become meters per second. And when you have meters per second plus meters per second, you get meters per second. So the units are working out. And if you put this in your calculator, you'll get the final velocity is negative 3.81 meters per second.
I think you can do that without a calculator.
That's true. You don't really need a calculator for this one because you're really just doing
That's true.
6 minus 9.81. All right. Let's do part B now. So how long after it was thrown does the ball hit the ground? So let me start by writing the knowns again. We have almost the same knowns. So this time, the initial position is the same, the initial velocity is the same. This time we don't know what time is, so I'm going to remove that. And this time we know the final position because it says that the ball is going to hit the ground. So the final position y is 0 because that's what we said the ground is. The ground is y equals 0. So we need to find t now.
T.
So let's take a look at our kinematic equations. But we're not going to use this because this doesn't have time in it. For this one, we don't know the final velocity and we don't know time. So that's two unknowns here. So we're not going to use this. For this one, we don't know final velocity and we don't know time. So I'm not going to use that. Over here, we have our initial and final positions. We have initial velocity. We have acceleration. So over here, the only unknown is time. So we can use this. So this is the equation we're using. We have y is 0 meters. So this can just go away.
I love it when that happens.
Yeah. So we got 0 equals, and y naught is 30 meters. I'm going to just ignore the units. And
I don't know, you capitulated like the rest of us.
yeah.
Too inconvenient to do with the units all the time.
And then initial velocity 6. And I'm just going to ignore the 0.00 also, just to keep it less clunky. So we got 6t plus 1/2 times ay. So that's negative 9.81 t squared. So I can clean this up a little bit. So 1/2 times negative 9.81, that's negative 4.905. And we have times t squared.
Interesting, you're putting the squared term first.
Yes.
And then linear term second. Then a constant is equal to 0. Oh dear.
Yeah. So I'm going to write it in standard form, math style.
Only if there were a formula to solve an equation of this form.
Yes, this is a quadratic equation. So doesn't look very fun to factor. So let's use the quadratic formula.
You're not going to factor it, Nick? Did you even try?
I'm
He
good.
doesn't need to. It's Nick. Come on now. He's just like that.
Yeah, so let's plug it in. So t equals negative b, so that's negative 6, plus or minus the square root of b squared, so that's 6 squared, minus 4a, which is negative 4.905, times c, which is 30, and now I'll put the square root, all over 2a, so 2 times negative 4.905. When you put this all in your calculator, you're going to get two solutions. So the first result you get is 3.16 seconds, and the other result is about negative 1.94 seconds.
That pesky fundamental theorem of algebra saying that a second degree polynomial is two solutions.
Yeah. So, which solution is physically meaningless?
I just watched Back to the Future, so I'm gonna go with the second option.
Yes. We can't have negative time, so we're gonna ignore that solution. So that's the time it takes for the ball to hit the ground. So 3.16 seconds. All right. Let's do part C. What is the velocity of the ball when it reaches a height of 20 meters? So again, let's write our knowns.
Well, we have the initial velocity. It sounds like we're looking for a final velocity.
That's right. These three knowns stay the same. We have the initial position, initial velocity, acceleration. This time, the final height, instead of hitting the ground and being 0, it's 20 meters. That's all we know, and we're trying to figure out the final velocity. So let's see what we can use. This one, we don't know final velocity, we don't know time, so we're gonna not use that. This one doesn't even have final velocity in it, so we're not gonna use that. This looks pretty good. We want final velocity, we have initial velocity, we have acceleration, we have final and initial position, so looks like we'll use this. And again, this one, we don't know time, and we don't know final velocity, so we're not using that. So, we want final velocity, but this is final velocity squared, so I'm gonna take the square root of both sides. And when you take the square root of both sides of the equation, we have to put plus or minus. But
Yes.
we can't have two different velocities at one height. So are we going to use the plus or the minus? Let's take a look at our picture. Over here, this is 30 meters. So it's going up and it goes down. And this is, let's say, this is the 20-meter mark. So is the velocity going to be positive or negative at the 20-meter mark?
The velocity would appear to be pointing in the negative direction.
Yes, it's going down since it's below the roof of the building. So we're going to use the negative square root. Initial velocity is 6. So we got 6 squared plus 2 times negative 9.81. And then the final position is 20. Initial position is 30.
Yeah, if you're not careful with your coordinate system, you could end up with negative numbers under that square root. So make sure you're paying attention to your coordinate system.
Yes, very
in your
important.
plans.
Very true. Very true.
So,
Do you have any comment on imaginary velocities?
well, if you get that the velocity is -3 plus 2i, you might have messed up. That's all I'm gonna say.
Maybe just a little.
Just
Yeah.
a little bit. So, if you put this in your calculator, you get about -15.2 meters per second. So that's a free fall problem. Pretty much one directional. So now that we did free fall, let's talk about projectile motion. Projectile motion is the motion of an object that is launched into the air and moves only under the influence of gravity. And again, we're assuming negligible air resistance. Before I actually talk about these equations, let's look at this graph here. This is the path of a projectile, and it's a parabola. And I picked 5 important points on this trajectory. Starting point, final point. I picked 2 points in the middle at the same height, and I picked the maximum point, the max height. The key to analyzing projectile motion is treating the x and y components separately. So let's start with the x component. Since we're ignoring air resistance, what do you think the acceleration in the x direction is?
Going by the note that you wrote above this graph where it said ax equals 0, I'm going to assume that ax equals 0.
Yeah, so since we're ignoring air resistance, there's no acceleration in the x direction. And since there's no acceleration in the x direction, that means that Vx is constant. It's not gonna, speed up or slow down. It's gonna have the same magnitude at every point. So I'm gonna draw Vx. Also, I'm gonna call this one V not x because it's like the initial point. But it's the same as Vx. That's actually one of the equations. Vx equals v naught x. Because, again, there's no acceleration in the x direction, so these velocities will all be the same in the x direction. Acceleration due to gravity is purely vertical, so gravity is not going to accelerate this projectile sideways. So if the object is projected at an upward angle, there's going to be an initial vertical component to the velocity, and we're going to call that v naught y. Let's say it's like this. And remember, acceleration is negative g.
It's also constant, so we can use these kinematic equations.
Exactly. Because of the downward acceleration of gravity, the y component of velocity is going to gradually decrease with time until the object reaches the highest point on its path. And that's where the y component of velocity will be 0. So Vy will be 0 at the highest point in the path. All right. So I'm going to draw Vy here, and it's going to be a little shorter. And this is just Vy, it's not V naught y. And over here, Vy is 0. And over here, it will be the same Vy as this point right here because it's at the same height, but it'll be in the opposite direction. So since the object is moving downward, Vy is now going to increase in the negative direction. Vy is going to become more negative. And same thing with this point right here. It's going to be the same Vy, but just opposite direction.
Don't do graphs, kids.
I drew the x and y components of the velocity, but what's the actual velocity vector going to look like? How would I figure out what the velocity vector is if I have the x and y components? So the velocity vector at any point is, hopefully the audience will understand, but it's vx I hat plus vy j hat. That's what the velocity vector is going to be. If you connect the vectors by placing the tail of this vector right here, the tail is just the base of the vector, and you place the tail of that vector at the tip or the arrowhead of this vector, then the vector sum is just going to be drawn from the tail of this vector to the tip of the second vector. So it's going to look like that.
It's basically just the hypotenuse of a triangle.
Yeah, yeah. And I'm just going to erase this too. But this will be the v naught vector. And it's
That's the first time I've seen that.
yes. By the way, these are not really vectors, they're components of this vector here. So when I said put the tail of this vector at the tip of this vector, what I really mean is this vector I hat and this vector j hat.
Like, what if v naught x equals blah 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 times I hat?
Well, I didn't put vector arrow though. This is just
Yeah, but you said in the first physics video, like, oh, we're not really gonna bother with that.
well,
Yeah, that is true.
okay.
The direction is
You want me
zero.
to put I hat here and j hat here?
Do what you want, Nick.
Anyway, so that's the initial velocity vector, and this is at an angle, let's call it theta naught. And I'll draw the velocity vectors for the other ones. So you can use the tip to tail method. So this is Vy right here, and you can, connect it and it'll look like this. Over here, there's no y component, so the velocity vector is going to be pretty much on top of the x component. So I'm not really going to draw that. And then over here and over here.
This is why every textbook starts with like an introduction to vectors.
Yeah. So notice how the velocity vector at each instant points in the direction of the object's motion at that instant. So it's always tangent to the path.
I was about to say it's tangential.
Yes. So think of projectile motion as free fall with an initial horizontal velocity. So we can analyze projectile motion as a combination of horizontal motion with constant velocity and vertical motion with constant acceleration. All right. So now let me go back to these formulas. These are the kinematic equations for projectile motion. So notice how there's no acceleration in the x direction. So if you go back to these general kinematic equations, if you let ax equals 0, you get this. Vx equals v naught x. This term goes away. You just get x equals x naught plus v0 xt. And these two will just end up being the same thing as what these two become. Oh,
Yeah, if it were up to me, I would just use the equations on the first page because these ones are just a special case.
yeah.
True.
So whatever your heart desires. And remember, these equations only apply to motion with constant acceleration. Okay, so one tiny thing I wanted to talk about is usually you're given the initial velocity, but you're not given the x and y component. You're not given v naught x and v naught y. So how would you?
Are you given the angle?
Yeah, you should be given the angle.
It's a trigonometry problem then.
Yes. So let's do a little trig now. We have this triangle. If we have the angle and the velocity v naught, we can find these components here. So we know that if we want to find v naught x, we can use cosine. So we know cosine of theta naught, cosine's adjacent over hypotenuse. So it's adjacent is v naught x, hypotenuse is v naught. So if I want v naught x, I just multiply both sides by v naught. So we get v naught x equals v naught cosine theta naught. And same idea for the y component, except now we use sine. So sine of theta naught is opposite, which is v naught y over hypotenuse. And to find v naught y, you multiply both sides by v naught. So v naught y equals v naught times sine of theta naught. All right. So I wrote these formulas here also. So if the projection angle theta naught is chosen relative to the positive x-axis, then these are the formulas you can use to find the x and y components of the initial velocity vector.
We love it.
Yep. So let's
Indeed.
do another example. A kid throws a rock with an initial speed of 10.5 meters per second at an angle of 49.6 degrees above the horizontal. Ignore air resistance.
It's crazy that he knew the angle and velocity.
Yeah. And find the position of the rock at 1.5 seconds. So I'm going to start by drawing a picture, kind of similar to this one right here. I'm going to make the positive x to the right. So x is in meters like this. And positive y will be up. And y is also in meters. The rock is basically thrown starting from x equals 0 and y equals 0. So its path is going to be a parabola like this. And we have the initial velocity. So we have v naught is 10.5 meters per second. And we have theta naught right here is 49.6 degrees. All right. So let's find the position. So let me write all the knowns. So again, v naught is 10.5 meters per second. We have the initial x position, x naught is 0 meters. We have the time is 1.5 seconds. The initial y position is 0 meters. We have the angle theta naught is 49.6 degrees. And since this is a projectile motion problem, and again, the object is under the influence of gravity, we can say acceleration in the y direction is negative g, so negative 9.81 meters per second squared. Yeah, that's pretty much all we know. So we're trying to find the position of the rock. There's x and y position, so our answer is going to be an ordered pair, x comma y for the position. So let's look at our equations. For the x position, let's look at this column right here. Looks like we're going to use this equation because it has x, and we know x naught. We don't know the initial velocity in the x direction, but we can find that using this formula right here because we know the angle and we know v naught. So we can use this equation, and we also have time. So let's use that to find x, the final x position. X naught is 0, so we can cancel that. V naught x, like I said earlier, we can just say that's V naught times cosine of theta naught. And we can plug everything in now. I'll include the units this time, so
I thought you'd finally changed.
yeah. Just this one time since it's simple. So V naught is 10.5 meters per second. Cosine theta naught, that's cosine of 49.6 degrees.
Cosine is unitless since it's a ratio.
Yeah.
Yes. And time is 1.5 seconds.
So the seconds cancel.
Yes.
And you're left with meters.
Very good. So that's what position is measured in. So that's perfect. So if you put this in your calculator, you'll get x is about 10.2 meters.
Make sure you put it in degrees, not radians, in your calculator.
Yes, very
Very, very, very important.
yeah. Now let's find the y position. Let's look at our equations here. So this equation doesn't have y in it, so I'm not using that. This equation looks pretty good. We have y naught. We don't know the y component of the initial,
You know that.
but we
You can find that.
yeah, we don't know it instantly, but we can find it using
The Navier-Stokes equation.
Actually, we do know it instantaneously.
Wrong.
yeah, we don't know v naught y, but we can easily find it because we know theta naught, we know v naught, so we can plug it into this formula here. And we know time, we know acceleration, so this equation looks pretty good. And we're not going to use this equation because we don't know the final velocity and we don't know y, so that's two unknowns. And same issue here. We don't know this, we don't know that. So we're using this equation to find y. So this is the equation we're using. Y naught is 0, and we know v naught y is v naught times sine of theta naught. All right, and then plus 1/2 ay t squared. So now we have everything here, so I just have to plug it all in. Okay, so this is with everything plugged in, and if you put this in your calculator, you'll get y is about 0.958 meters. So the final answer for the position is going to be x comma y. So 10.2 meters, comma 0.958 meters.
Well done. Very nice.
There you go. So that's going to be the position after 1.5 seconds. All right, let's do part B now. Find the velocity, magnitude, and direction of the rock at 1.5 seconds. Let's go back to our equations. Velocity, this looks pretty useful for the velocity in the x direction.
Indubitably.
So we can use that. And I'll get to y later. So get to the y component later. So v,
You start with the what before you start with the y.
yes.
True.
So the final velocity is the same as the initial velocity because in the x direction, there's no acceleration. And we know the initial velocity is just v naught cosine theta naught. So we just gotta plug everything in. By the way, the knowns are the same as last time. It's the same time. You're gonna get 10.5 meters per second times cosine of 49.6 degrees. If you put that in your calculator, you'll get Vx is about 6.805 meters per second. And I'm keeping an extra digit because we're going to use this later to find the velocity. Now let's find the velocity in the y direction. This doesn't have Vy in it, so I'm not using that. This looks pretty good because we can find this using V naught sine of theta naught, and we have acceleration, we have time, so that's good. This one looks good too because we have the position from the last problem. We have all these.
This equation's uglier.
But this equation is uglier. So we'll stick with this one. This one's the easiest thing we can use.
As we know, physics is all about being pretty.
Yes. So
You got to look good while you do it.
that's right.
Oh.
V naught y, we know that's V naught sine theta naught. So I just gotta plug everything in now. I'll just ignore the units for now. And if you put this in your calculator, you'll get Vy is about negative 6.7188 meters per second. Okay, so that's the velocity in the x and y direction, but we want the velocity overall. So how do we find the magnitude of a vector given the x and y components?
You just do a little bit of Pythagoras, you know?
Yes, we know that v squared equals vx squared plus vy squared. This is basically a squared plus b squared equals c squared. Basically, to find the magnitude of a vector, you take the square root of the sum of the squares of its components. Vx squared, that's 6.805 squared, and vy is negative 6.7188, and we're going to square that too, and I'm going to take the square root. So you'll get v is about 9.56 meters per second. So that's the magnitude of the velocity at 1.5 seconds, but we also need the direction. We need theta. If we have,
Could I?
sure,
Okay, well, the answer is the arctangent of Vy over Vx.
yes, we have v, we got vx, we got vy. So this is the angle. So tangent of that angle is going to be Vy over Vx. It's going to be opposite over adjacent. So tangent theta is Vy over Vx. So we're going to
Is
use,
theta or theta not?
this is just theta. That's a good question because this is the angle at 1.5 seconds. Theta naught is the angle at 0 seconds. It's the initial angle. So I'm going to use theta for this angle at 1.5 seconds. So take inverse tangent of both sides. So you get theta is inverse tangent of Vy, which is negative 6.7188. That's why I kept an extra digit there because we're using these numbers again, divided by Vx, which is 6.805. In degrees, you'll get theta is negative 44.6 degrees. So negative angle, that just means that it's below the horizontal. Basically, we're at this point right here. We have Vx to the right, Vy pointing down, and we have this angle here below the horizontal. So I'm going to write, comma, 44.6 degrees below the horizontal. All right, so that's the magnitude and direction of the velocity at 1.5 seconds. All right, now part C. What is the greatest height above the ground that the rock reaches? Let's write our knowns. Let me just copy paste this and see what changes. So this time we don't have any information on time. Everything else stays the same. We have v naught, we have x naught, y naught, theta naught. We know acceleration is negative g. But one new thing we know, remember at the greatest height,
The height of that arrow is 0.
Vy equals 0 at the max height. That's very important here. So I'm going to add that in. And we want to figure out the greatest height, which is y. Y equals what? Let's look at our equations. This equation doesn't have y in it, so we're not using that. We don't know time, and we don't know y, so that's two unknowns. We're not using that. We know the final velocity is 0. We can find the initial velocity using v naught sine of theta naught. We know ay. We know y naught. We can find y here. We just got to rearrange. So this is looking pretty good. And this has time in it, and we don't know that, so we're not going to use that. So y naught, 0. Vy, the final velocity is also 0. So we can rearrange and find y. So we got 0 equals v naught y, remember, is v naught sine of theta naught, and we're squaring that, plus 2ay times y. If you solve for y, we just subtract v naught sine of theta naught squared and divide by 2ay. And you'll get y equals negative v naught sine of theta naught all squared divided by 2ay. If you put this in your calculator, you'll get y is about 3.26 meters.
We found the answer that we were looking for.
Yes.
Indeed.
Let's do part D now, the final part. My favorite problem. Find the horizontal range R. So if you don't know what range is, this is the horizontal distance from the starting point to where the rock hits the ground.
It's just horizontal distance, basically.
Yeah, like I'll label it on here. This is
I call this quantity delta x normally.
yeah, basically this distance right here, that's going to be R from the starting to the ending point, like a delta x. Yeah. We need to find x. So this is the equation we got for x here. The problem is we don't know time. V naught x, we know that. That's just V naught cosine of theta naught. But we don't know time. Let me actually write all the knowns. Here, these are all the knowns, but we just don't have time.
We don't have time. There's never enough time.
Yeah, there's never enough time. So we need to find time. And once we find time, we can plug it in here and find x. We can find the final x, which is r. To find time, we have to look at the y component because the time for x and y component are the same. They're the same t's here. So let's see what we can use. We're not using this because this doesn't have time in it. Just one other thing,
Yeah.
we know that the final y is going to be 0. It starts and lands in the same height, which is 0. Then we can say y is 0. So
We can.
let me look at the equations again. We're not using this because it doesn't have time in it. Over here, we can use this, but
Yeah, the second one could get a little bit quadratic.
Just a little bit.
well,
It looks like by process of elimination, you were going to use the first one.
That's what I was thinking.
yeah, this actually won't be that bad because these are both 0 and you can divide by t.
Go with the first one, though. Go with the
Yeah,
first
the
one.
first one, sure, we'll use the first one, but we don't know Vy, but
I think we do know it.
we kind of do because it just, remember back here, this is
It's
just
just the negative of the initial.
exactly, yeah, just
Um,
opposite magnitude of the initial velocity. There's some flexibility here, but I'm going to go with the first equation. So we're going to find t, and then we can plug it in here and find x, which is the range. Let's rearrange. So we have t. We're going to subtract v naught y and divide by ay. So vy minus v naught y divided by ay. Vy, remember, the final velocity, because the trajectory is symmetrical, we can say it's the opposite of the initial velocity. And yeah, we're dividing by ay. Negative v naught y minus v naught y, that's just negative 2 v naught y. And v naught y is v naught sine of theta naught. I'm actually going to keep it in variables for as long as possible. So
Yes.
this is the time.
that's what I was thinking you should do.
Yeah.
Finally, something I agree with that Nick does.
So this is the time. We can plug it in to this equation and find x. So x is the range. So I'm going to call that r now.
Oh,
X naught.
really?
Yep, it's the final x position, which is r. And
Gotcha.
and x naught is 0, and we got v naught x times t, which is this thing right here. So v naught x is just v naught cosine theta naught. So I can put that in the numerator. So negative 2. We have v naught times v naught, so that's v naught squared. And we have sine of theta naught, and we have a cosine of theta naught now. This is v naught cosine theta naught right here. So we have v naught squared, and we have sine of theta naught cosine of theta naught divided by ay. And we will use a double angle identity to make
I love this part.
yes, to make it look
I
nice.
hate it.
So
Finally, a question where Nick does everything the way I want him to do it.
we got 2 sine theta naught cosine theta naught right here. So that's just sine of 2 theta naught. One more thing we can do to make this even cleaner is we know AY is just negative G.
So the negatives are gonna, I like it.
Yeah, this negative will
Yeah,
go
me
away,
too.
and this will just be over G.
That's a good answer.
So
It is. Vossen taught 2 over G.
So this is as clean as it gets, and you can use this formula if you're trying to find the range for any problem, as long as the initial and final height are the same. But usually it's not really given in the formula sheets. It's kind of something you got to derive.
I think it's more fun to derive it or memorize it, but more
Yeah.
fun to derive it.
That's true.
I feel like it's less fun actually.
Anyway, but let's plug everything in. And if you put this in your calculator, you will get the range is about 11.1 meters. So that's how far the rock travels horizontally.
Wow,
Wow.
that's a lot of meters.
Yep. That is it for today.
Yeah,
So,
man. Thank you guys for watching today. This was a great lesson on my brilliance and just how far above I am in the world of physics, above everyone else. So have a great rest of your day, guys. Make sure you smash that mother like button. You hit that subscribe button and you ding, 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 ring the notification bell so you never miss an upload, right? And until next time, guys. See ya.
Bye.